root 2 is rational. We'll make that assumption. And from it we will deduce, we will logically show that we get a contradiction. Now how to do that, right? So, so A and B are integers, okay? A and B have no common factors, right? So we don't want things like this. We don't want like 4 over 6, because you can simplify that down to 2 over 3. Okay, so we're assuming that our rational number here has been simplified as far as possible. All common factors that are in A and B, they've all been removed. They've been divided out. Okay? So we've got rid of this kind of thing. So we don't have 4 over 6, we'd have something like 2 over 3. The 2 and 3 have no common factors, so that's important, right? That we have a rational number that's been simplified to have no common factors. Common factors for A and B. Now, we will now show that this is actually false, that they do have common factors. If this is true, we will contradict this. So let's do that. So let's prove it. All right. So let's assume that this is true, and that A and B have no common factors. So let's square both sides, and we'll get 2 over A squared is B squared. Okay. Take the B squared over, so 2B squared is A squared. Right? And that implies, now this left-hand side is even, right? You've got a 2 times something, so whatever it is, whatever the B is, A and B are integers, remember. So the left-hand side is even, so the right-hand side is even. So A squared is even. Now if A squared is even, A is even. Did we? Well, I haven't proved that, but it's not too difficult. You could prove that yourself, right? So if A squared is even, A is an integer, therefore A is even. And that means that A can be written in the form, let's say 2C, right? Where C is an integer. All right, we'll plug in that here. So you've now got 2B, plug this into here. So now 2B squared is A squared. Well, that's 2C squared. So that's 4C squared. And that means that B squared is 2C squared. Follow that? Okay. So that means, and that implies B squared is even, because this is even. B squared is even. So B squared is even. And that implies, just the same logic, B is even. Right? So therefore you can write B in the following form. B is 2D. Okay? And where D is an integer. Now look, we've just shown that A is even and B is even. So A has a common factor of 2 and B has a common factor of 2. So they both have a common factor, namely 2. Right? That contradicts this, because we assume that it has no common factors. So we've now got a contradiction. Let's call this statement P. And from these two, we have got not P. We've shown that A and B do have common factors. So we've got a contradiction. So something's wrong. Well, what is wrong? Well, the original assumption, this, that root 2 can be expressed as root 2 is a rational number. That's the contradiction. Right? That's what's wrong. So we reject that. Okay, that's a concrete example. Now let me try to give you the actual general proof, and it involves a bit of symbolic logic. I hope you've done some of that a little bit. If you haven't, it's not too difficult. So so what I'm giving you now is the general proof of what I've just done here, which might have seemed a bit flaky. So here it is a bit more rigorously done. You're given some mathematical statement, P. As an example, that's a mathematical statement, right? The product of 3 consecutive integers is divisible by 6. That's a you're stating that, you're saying that is true, right? So in general, let P be a mathematical statement. And you're trying to prove that if P is true, then Q is true. So Q is just another mathematical statement. For example, if A squared is even, then A is even. In fact, well, okay, I actually use it here. So that might be an example of a statement, call it P. And that's a different mathematical statement, call that Q. Right? So if P is true, then Q is true. Right? So we're trying to prove that Q is true. Right? We start with P, that's a given. That's one of your premises, if you like. So if P, then Q. Okay? Now, if you're going to prove something by contradiction, by RAA, you take what you're trying to prove, in this case Q, whatever it is, some mathematical statement, and you assume, for the moment, for the time being, you assume the opposite, right? So let's assume that not Q is true. And then we try, using this as a premise, to deduce, using logic, not P. Okay? And if we can do that, we have P and not P. We have a contradiction. You can't have both, right? You can't have P and not P at the same time. That's contradictory. So if we can deduce not P, then not Q must be false. So if not Q is false, then not Q is true. But not Q is just Q. Okay, let me sort of spell that out a bit more. Okay. Right. So you start with this. You make the assumption. You're trying to prove that if P is true, then Q. So let's assume that not Q, the opposite, is true. And from that you deduce not P. So here it is here. Start with not Q, right? And you deduce, logically, you get not P, right? But, in general, P is the same as not P, right? A double negative, not something, is just the something. Not something is something. That's what I'm saying here. P is the same thing as not P, right? Now, let's call not P B. So you've got not P is B, so that's the same as not B, right? Now in general, if A is true, then B is true. Let's assume that. So if B is false, so not B, therefore A must be false, right? So not A. I'll give you a concrete example. I'm living in the Chinese city of Xiamen. Xiamen is in China. So if I'm living in Xiamen, I'm living in China. Therefore, if I'm not living in China, then I'm not living in Xiamen. Makes sense? Just common sense. If I live in Xiamen, I'm living in China. but I'm not, imagine, but I am, but imagine, but I'm not living in China, therefore I can't be living in Xiamen, because Xiamen is in China. Okay? So this is true in general, right? So if I let that be statement A, I let not Q is A, and I let not Q is, let that be B, and so I've got this here, right?